Hi students, welcome back. We are now moving on to faults within our Crustal Deformation unit here. So we are going to start talking about when rocks are experiencing brittle deformation and they start to break. All right, so first things first, faults are some sort of displacement of rocks, right? So we have two rocks or one rock that is being split into two and shearing apart. Okay, this can happen vertically or it can happen horizontally. If it happens vertically, we call those dip slip faults. If it happens horizontally, we call those strike slip faults. So with dip slip faults, we have normal and reverse, and they are driven by two different types of stress. With strike slip faults, these are all driven by shear stress, and they either move right or left. Okay, so with dip slip faults, again, we have an up and down movement or a vertical displacement of rocks. And so because we have a vertical displacement of rocks, we have to be able to label which rock is on top of which. And sometimes this can be tricky, especially in the field when you're actually looking at rocks that have been displaced. And so what we do is we use a man that stands in front of all of our faults. I call him Homer. You can name him whatever you'd like. We'll see him pop up a couple times throughout this video. But he stands in front of the faults, and wherever his head is the hanging wall block, and wherever his feet is the footwall block. Okay, so because we can orient ourselves using the hanging wall block and the footwall block, then we can talk about which one is moving up and which one is moving down. Okay, so remember, if you're working with a diagram and you're trying to figure out what type of rock you're looking at, fault you're looking at, you want to draw a man standing upright. Don't put him in line with the fault because then it doesn't work. Cross the fault, standing upright, and then you can decide which one is the footwall block and which one is the hanging wall block. And so in your work this week, I did include a fault block model for you to work with, and you can work with it throughout this lecture, and then you can play with it at home because it does definitely help you see how things are moving. And so this is one that's actually completed. You'll cut it out, you'll print it out, then cut it out, color it, and then you'll be able to move the pieces side by side. And this should be approximately your end result. If you want to color them different colors, that is totally fine. There's just some suggested colors there for you. Okay, so with normal faults, this is driven by tensional force. So things are being pulled apart here. They're experiencing tensional stress. And what happens is the hanging wall moves down. So you can see in that diagram or that GIF that they were once together and one of the blocks is moving down. If you were to draw your man, or it could be a woman if you want a woman, whoever you want person to stand in front of your faults, if you draw a person in front of your faults, then you would see that on the right-hand side here, their head would fall into that block and their feet would fall into the block on the left. And so the block that's moving down is the hanging wall block. Okay. And so you can do this with your diagram. There's some directions for you on how you move your little block diagram in this manner and see what you observe. All right, so here, the way that we look at these in the field is we use marker beds. And so there are some black marker beds here that these arrows are pointing to that are offset. And that offset distance tells us how things are moving. So we identify the fault, which is the red line, and then we identify the marker bed showing us the displacement or the offset of that layer. And so we can see that on the right-hand side, it has moved up, and on the left, it has moved down. And so if you draw Homer or your person in front of the fault, you can see that the hanging wall block is on the left and the footwall block is on the right. And so the footwall block is moving up in this instance, and the hanging wall is moving down. So we call this footwall up normal, or FUN. It's a fun little acronym for you to use. Okay, so with normal faults, we have a situation in which we might see alternating direction of these faults. And when that happens, we get something called a Horst and a Graben. And so as you see in this diagram, we have normal faults that are tilted away from each other and toward each other. If they're tilted away, that means that the hanging wall block is in the center for both of them. And so that center block will drop down into what we call a Graben. In the opposite, where they tilt toward each other, you would see a Horst where the footwall block is in the center there for both of them, and both of them would uplift in the center, and we get a mountain, and the Graben would be our valley. If we see a series of these, we can see a full landscape of ridges and then valleys, ridges and valleys, mountains and valleys. And we do have that in California called the Basin and Range. It starts on the eastern side of the Sierra Nevada, along the Sierra Nevada Frontal Fault System, which is the first normal fault in this sequence of a bunch of normal faults that run through the Basin and Range. Now, we talked about vertical faults or dip-slip faults that move up and down from tension, which are normal faults. Now we're looking at compressional forces here. So we have compression of the rocks, and that creates... Okay, so here we have compression forces pushing against these rocks. We have a normal rock block there with a bunch of different horizontal layers, and as compression is applied, they break, and one of them is pushed upward. And that one that's pushed upward happens to be the hanging wall here. And so with your little diagram, you can move things around and watch as you move the layers up on one side, what is happening to the layers, what are you creating, basically. So if we look at a fault in the field, again, we have those marker beds that we're using. There's black horizontal marker beds here. And so those marker beds have been offset. You can see where the fault transect is. You can draw your person in front of the fault, label where the hanging wall is and where the footwall is, and then look at what is happening. So here you can see that the hanging wall is moving up and the footwall is moving down. And so a good acronym for this is HER, hanging wall up, reverse. So if you remember FUN and HER, you can remember the difference in movement between the reverse and the normal faults. In California, there's a few different reverse faults. One of the most notable in Southern California is the Sierra Madre fault zone. And so this is in the LA Basin, and it helps uplift the San Gabriel Mountains. Within reverse faults, we have a couple of more specific situations in which we call them something a little bit different. So with reverse faults, if the dip angle, so we talked about dip already in Crustal Deformation lecture, the dip angle of the fault, if it's less than 45 degrees, we call it a thrust fault, where material is really just being thrust over other rocks. And so if you see a fault called like the Mount Diablo thrust fault, they're talking about a reverse fault with a dip angle less than 45 degrees. If it's more than 45 degrees, we just call it a regular reverse fault. And so in California, here is an example for you. It's at Mount Diablo in kind of the north of San Francisco Bay Area. In addition to that, we can have thrust faults that don't actually come to the surface. And so when that happens, we end up with what we call a blind thrust fault. So material is moving over other material and being thrust upward from compression, but it's not actually breaching the surface. And so we don't see displacement at the surface. We might see one of those monoclines at the surface, those little step folds, and then there might be a blind thrust underneath. These are really dangerous because we can't see them at the surface. We don't see their surface offset in an obvious manner. And so in the 90s, the North Ridge Blind Thrust Fault in San Fernando Valley was actually discovered from a pretty major earthquake that they experienced in the area. So without knowing that that fault was there, which is why we call them blind thrust faults, they don't exhume themselves at the surface, so they are not necessarily known until we have an earthquake occur. Okay, so those were all the dip slip faults. Those are all the things that move vertically. Now we're looking at things that move horizontally. So these are your strike slip faults. They move side to side, okay? So they are driven by shear stress. So rocks are being sheared apart here. These are associated with your transform plate boundaries, okay? So here we either see right lateral or left lateral. The best way to tell which type you're looking at is by aligning yourself parallel to a feature that is offset. So here there are a couple of roads that are offset by the faults. And if you align yourself parallel to that road, perpendicular to the fault, but facing the fault, okay, so you imagine you're the red car, for example, and you're driving down the road. On the left-hand side there, the first diagram, you approach the fault and the fault has displaced your road, okay? Which direction has it displaced the road? Where do you have to turn to get to the rest of the road? You have to turn right. So that is a right lateral strike slip fault. On the bottom right there, if you're in the red car, you're driving down the road, you get to the fault, it's displaced your road, and it's displaced it to your left. So you'd have to turn left. Okay, so you want to make yourself parallel to the feature that is offset, perpendicular facing the fault. When you do that, if it's on your right or it's on your left, that tells you if it's a right lateral or left lateral strike slip fault. Right, so we do have the big San Andreas Fault in California that separates the North American plate from the Pacific plate as they interact and move and creates a lot of horizontal offset. So if you align yourself on this fence here that's in the center, you want to be perpendicular to the fault, facing the fault, parallel to the feature that's offset. You notice that the rest of the fence is to the right. It doesn't matter whether you are facing into the page or out of the page, whichever fence you pick, it's always to the right if you are facing the fault. You can also see this at Wallace Creek in the Carrizo Plains in Central California, Central West California. And if you look at that creek that's down the bottom left there, you can align yourself with the creek, perpendicular facing the fault, and you can see that the rest of the creek is to the right. Okay, so the creek is a natural offset feature, whereas the fence would be some sort of man-made feature that's offset. So most of the features that we see that are offset over time is stuff that's man-made because they're really easily broken, whereas the creek would take a very long time to actually see the displacement along a creek. And creeks and rivers move and are dynamic as well. So even if a fault was displacing it, it might actually realign itself so you can't actually see that displacement anymore. All right, so just like with the folds, we need to be able to identify what faults we are looking at. So I want you to take some time to look at these 3 different pictures and try to decide what type of fault you are looking at. Make sure you're looking for marker beds and things that are offset. Note that all of them except for B are actually in cross-section view. B is in map view. Okay, so remember that when you're looking for vertical displacement or you're looking for horizontal displacement. All right, so we talked about the different types of faults. The dip slip faults move up and down or vertically. We talked about the strike slip faults which move horizontally. So with dip slip faults, normal is driven by tension, reverse is driven by compression. Strike slip faults, both right and left lateral, are driven by shear stress. Okay, and all of these are caused from brittle deformation of the crust. Okay, so next we are going to talk about earthquakes, and I will see you guys in the next video. Bye.